This part 3 of tutorial uses the PIC4 to demonstrate how to debug the project, testing each line of code discussed so far. The snap programmer may also be used. An actual device is used with the PIC4, wired up as discussed in the intro, so allowing the actual pin states to be monitored and manipulated by the lines of code. Remember to add jumper wires between top and bottom power rails. Add the external 5V and ground supply if used. The PIC4 can be used to power this circuit, then no external supply is required. The snap, however, requires the external power supply. The breadboard tutorials PIC16F1705 Ep6 LED discusses these setups in more detail. This will allow the code to be stepped through and the values of file registers being changed clearly followed. Part 4 of this tutorial will use the simulator to emulate the program without the need for a PIC device or programmer, so be sure to look out for this tutorial. Now let us set up for debugging and run through what has been covered to this point. Select the project properties icon, and here is the setup using the PIC4 or if using the snap option. Again refer to the PIC12F1572 Ep5-1A LED for the PIC powering the circuit or being externally powered. Now with either the PIC4 or snap setups complete, we can continue setting up for debugging. First add a breakpoint at line 61. This is done by clicking on the number to add the breakpoint as seen here. This will halt the program at this point once debugging the program has been initiated. Select the debug project icon to start the debugging session. An output window will confirm the programming complete, breakpoint set, and the target halted. Close this output window and then note the green arrow at line 61, indicating the halted position of the debugging session. Now open a debugging variables window from this menu selection displayed. Click in the Enter New Watch and fill in all the variables indicated here, starting with the first variable, oscon, through to let's. Then open a file register memory window using the menu displayed here. The file register window may open up here, so click on the file register tab as indicated, holding the click button and drag the window down to the bottom and right side till the area to reposition is highlighted as indicated here. Next, select the form drop-down to select symbol to change the registers to symbol as displayed here. Next, click on this icon to open up the required columns to display and deselect the char to remove this column. Column widths and positions can be adjusted. So now we have set up the variable and file register windows for this debugging session, and the program is halted at line 61. The continue icon or F5 can now be used to resume the running of program. The pause icon can be used to pause the running program. Now the reset icon can be used to reset the device, and the reset vector address hex 0 is where the program now halts. Check the file register window, address 002, symbol PCL for the program counter value, here 0 hex. The step into icon or F7 executes one line of code from the go to start label. The start label then jumps to line 61. Note the file register window indicates the program counter value has now jumped to hex 4. We will have a look at another debugging window called the disassembly window later to explain the program counter value when we discuss the main program and delay routines. Another step into, or F7, executes line 61 and moves to the next line of code. Note the file register window program counter value now at hex 5. The file register window address 008 for the BSR or bank select register has now changed to hex 1, confirming that the memory bank select register has selected bank 1 in which the OSCON register is found. See page 45 of datasheet for more detail. Line 62 will move a literal value of hex 68 into the working register once F7 is used to execute the line of code. Note the file register address 009 for the working register value is hex 10 before the line 62 is executed with the F7. Also note the variables window OSCON register has the hex value of 99 or binary value of 00111000, which confirms the default value for the IRCF bits 3 to 6 are 0111, which is the default system clock frequency for the 500 kHz after a reset for the PIC16F1705. Another step into, or F7, executes line 62, which loads the hex value 68 into the working register and moves to the next line of code. The working register now holds the value of hex 68 or 01101000, and the program counter value has incremented to hex 6. The next instruction is executed with another F7, which now transfers the working register value into the file register OSCON. The variables window now indicates the OSCON register holds the binary value 01101000, which contains the 1101 for bits 3 to 6, confirming the IRCF frequency has now been adjusted for the required 4 MHz system clock used for this tutorial and the delay routines we will still explain later. The program counter has also incremented to hex 7. The modes for port A and C are next. When this line of code is executed with F7, the bank cell ANSL A selects the memory bank number 3, which contains the ANSL A special function register. The file registers window address BSR also confirms the bank 3 has been selected with the hex value 3, and the program counter increments to hex 8. Note the value of ANSL A in the variables window is hex 17 or binary 10111, which has RA0, 1, 2 and RA4 bits defaulted to the analog mode, or 1s after a reset. RA3 is digital mode, or 0, due to the MCLR function set up for this pin in the configuration words. The line 74 is executed with F7 and the ANSL A register is cleared to 0, putting all bits into digital mode from the default analog mode. The variables window also confirms the ANSL A register now has all available bits RA0 to RA5 at 0 for digital mode. ANSL C follows the same process, clearing all available bits RC0 to RC5 for digital mode. Port A and C directions are set up next using the TRIS special function register. Bank cell selects memory bank 1 for TRIS A. Then move literal value hex 1F is loaded into the working register. Hex 1F has the first 5 bits 0 to 4 as 1s for inputs, and the 6th bit is a 0 for the output, required for the LED control on or off. The literal value held in the working register is then moved into the special function register TRIS A, with the next F7 executing this line of code. TRIS C follows the same process, loading 3F into the TRIS C register, which sets all available bits RC0 to RC5 for inputs. Port A and C weak pull-ups are set up next using the WPU special function registers. First, the option reg bit 7 needs to be cleared. Bank cell selects memory bank 1, which contains option reg special function register. The bit clear file register instruction is used to clear the 7th bit of the option reg, with the F7 executing this line of code. Now the bank cell WPUA selects memory bank 4, which holds the special function register weak pull-up for port A. The hex value 1F is loaded into the working register and then moved into the file register WPUA. This sets the first 5 bits 0 to 4 to 1s, which enables weak pull-ups for these specific pins, and the 6th bit is cleared to 0, disabling the weak pull-up not required for the output on RA5 pin. Weak pull-ups for port C follows the same process, loading 3F into the WPUC register, which sets all weak pull-up bits RC0 to RC5. This maintains high states for these unused pins. Port A and C initial bit values after a power-up or reset should all be high or 1s. We follow the datasheet's example 11-1 on page 119 of initializing ports to finish off with. Clearing port A and port C, as well as lat A and lat C. Having already cleared ANSL registers, we skip this. Then I purposefully load the hex literal value 3F to the port registers to demonstrate the latch, port, and weak pull-up register operation, and expected differences between port A and port C explained. This ensures RA2 and RA5 bits are set high to match the switch input when not being pressed, and LED output state, keeping the LED off at power up or after a device reset. Now let's go through these lines of code and confirm the registers as we proceed. Bank cell selects memory bank 0 for port A, and the CLRF instruction clears the port A file register, or does it? Having a look at page 119 of the device's datasheet, section 11.1.1, data registers, there is mention of the writing to the port register, which entails reading port pins, the value then being modified and then written to the latch register. This is precisely what we see when the CLRF instruction is executed with an F7. The CLRF of port A reads pin values, modifies, and in this case clears port A bit 5, and also clears the latch register. Only port A bit 5 is modified during this executed instruction, which may seem strange, but will become clear once the other bits are discussed during the following instructions. The next instruction selects the memory bank 2 for the lat A register, followed by the clearing of the latch register. See page 118 for an explanation of a write operation to the latch register, having the same effect as writing to the port A register, which is not quite what seems to happen for the CLRF instruction of lat A, but let's take a closer look. After executing the clear file register lat A with an F7, let's check port A bit states. RA0, RA1 and RA3 bit states are dependent on the debugging functions during the debugging session, so ignore them. RA2 circuit is expected to remain high, being connected to the pull-up 10K resistor and 5V VCC. RA4 weak pull-up has been enabled, so this bit is expected to remain high. RA5 bit state is already low, since being modified during the execution of port A CLRF instruction. This bit is digital and an output, so the lat A CLRF instruction does not need to clear any bit states at this point. so port A bit states at this point have been discussed. But let's look back at port A bits from the start of the debugging session to discuss some other points not yet covered. When the breakpoint halted the program at line 61 at the start of the debugging session, only bit RA5 was high. RA5 bit is high due to the actual voltage on pin being around 3.4 volts. The 5 volt VCC supply connected to the 1K resistor and then through the forward biased LED maintains the 3.4 volts on this pin, keeping the pin state high. Port A pins RA0, RA1, RA2 and RA4 are low due to them at this stage being in analog mode, and digital reads will be read as 0. RA3 having been set up for the MCLR function in the configuration words and its bit state indicated as 0 here. Once the ANSL A register is cleared at line 74 and the bits are read as digital, RA2 is now reflected as being high as expected, as it is connected to the 5 volt VCC through the 10K resistor, so pulled high until the connected switch is pressed and pulls voltage low. Then after option reg bit 7 is cleared at line 98, RA4 bit is then shown as high with the WPUA4 bit by default enabled, so pulling this bit high. The weak pull-up port A bits are loaded with 1F after line 102 is executed, so enabling the weak pull-ups for bits 0 to 4 and disabling RA5 bit for the required RA5 output function for LED control. When port A bits are cleared of line 113, this pull-up keeps RA4 pin high, demonstrating the internal weak pull-up functioning. Another effect of port A bits being cleared of line 113 is that the port A RA5 bit is also cleared at this point. Only RA4 and RA2 are high, so that when the clearing of the lat A register of line 115 is executed, no changes are highlighted red. From here, port A is loaded with the 3F hex value, and once line 118 is executed, the RA5 bit is also kept high, so keeping the connected LED off as required after a reset or power up. Port C follows the same process, clearing port C, which is reflected by all bits of the lat C register being cleared to 0. The lat C register is also cleared, but this time all bits are held high due to the weak pull-ups having been enabled for port C. Port C is also loaded with the 3F value, and the lat C register confirms all bits are set high as expected. This concludes the debugging session of the devices set up to this point using the PIC4 and actual PIC device. The next part 4 tutorial will be covering the use of the simulator where no PIC device or programmers are required. The delay routine is looked at and we use the IDE stopwatch to confirm the delay period. We also go through the subtle differences required to use the simulator to debug. So be sure to like, subscribe and hit the notification bell to receive updates on the next tutorials as they become available.